And basically, the purpose of the circuit is to process or to manipulate signal so that you can see or hear the signals with your eyes and ears. Yeah? Again, like I said, it would be nice if your eyes can see the video without having a system, electronic system. Huh? Maybe somebody can discover, put something, implant something into your eyes. Then you don't need a TV, you don't need a computer, right? You can see the video directly. Like that. So, okay, so now you need an electronic system to see and hear. And this electronic systems consists of many circuits. Okay, now, all the circuits we are talking about can be grouped into two types. Okay? So, there are two types of circuits. The first type is the circuit consisting of passive components such as resistors. We call this capital R, capacitor, we call this capital C, and inductor, we call this capital L. Okay, so this is the first type. The second type of circuit, again, I turned it very large, right? So for those of you sitting on the back. For the second type of circuit is the circuit consisting of active components such as transistors. In addition to R, L, and C. Okay, so sometimes we call this the first type of transistor as the linear circuit. The circuit. It's called linear circuit. And the second type of the circuit is called the nonlinear. Now, 99.9% of the circuit we are using in the electronic system are non-linear circuits. Okay? So that means in this type of circuit, you have the transistors plus the RLC components. You know what's a transistor, right? No? What's a transistor? You never learned transistor in your physics class? No?
Oh, that's physics too.
Okay, let me see how I can explain it. Well, a transistor is a device. It is made of silicon. You know silicon? That's the silicon, right? We use to make all the transistors. Okay. So silicon is a semiconductor material. When I say semiconductor, means the conductivity of the material is neither a conductor nor the insulator, right? So the conductivity is between the metal and the insulator. Okay, now why do we use silicon to make transistor? That's a long story, I don't want to get into that. Right? But we use silicon, okay, and then with many different steps, we can make different transistors. Okay, the major functionality of a transistor is to amplify the signal. Okay, is to amplify the signal. Okay, we call it amplification. So, if you have a circuit that consists of transistors, then that circuit can be used to amplify the signal. Now, why do we need to amplify the signal? Huh? Yeah.
Because it loses power as it goes through the system.
Yeah, because for example, the music signal that is in the air that was broadcast by the radio station, right? When you capture it with your iPod or your radio, okay, the signal is normally very weak, and that is not audible to your ears. Right? So you have to amplify it. So that's one of the main functions of the transistor. So that's why you need this type of circuit, right? Most of the time is to amplify the signal. But it's not the only function you be looking for. Sometimes you want to do other things. Okay. For example, you may want to change the signal from the digital to analog. You know what's analog but digital, right? That's good. All right. So therefore, in some of the systems, you need a to D or D to A converters. A means analog, D means digital. Right? So that means if you have A to D, that means you are converting analog signal to the digital signal. Yes? Okay. Now, and that converter also has a lot of transistors inside of it. It's a circuit. Okay, converter is a circuit. Right? Okay. So that's also a different function. Right. But for this class, we are not going to talk about the nonlinear circuit. We're going to be focusing on the linear circuit. So now, I just mentioned, right? 99.9% of the circuits are nonlinear circuits. So why are we studying the linear circuit? Well, if we do not understand how a linear circuit works, then you will not be able to understand how a nonlinear circuit. Okay? So therefore, this is the first step, okay, for understanding the circuit. Now, because you are not electrical engineering major, so therefore, I guess the university decided that we should learn something that's more fundamental, and that's why we are learning the linear circuit. If you were changing your mind and become an electrical engineering major, then you'll be required to take the nonlinear circuit class later. Yeah? Okay. And you can see that for the nonlinear circuit class, you have transistors, you also have RLC. Right? So therefore, these are embedded in the nonlinear circuit. So therefore, we have to understand this before you can do this. Huh? All right. Now, the components we are talking about for this type of circuit are the resistor, the capacitor, and the inductors. So basically, we're going to try to understand how to analyze the RLC circuits in this class. Now, the signal can can be represented in terms of the voltage and the current. Okay, so last time I also mentioned briefly about the concept of the voltage and the current, right? So basically, if I have two places, okay, and I have a lot of charge in one place, and I have no charge on the other place, then this place with a lot of charge would have a higher electrical potential. Okay? So this has higher potential. And sometimes the potential is also called the voltage. Huh? Okay, and this place that has no charge, then it has a lower potential. Right. Then, if I somehow connect the two places with a conductor, okay, a metal, then the charge will be able to flow from the higher potential to the lower potential. It's very much like the concept of the flow of water. Got it? Okay? So, but this has to be a metal. You cannot put an insulator, because insulator does not conduct the flow of charge. This reminds me about an interesting phenomenon we see every day in Florida, in summer. What is it? Lightning. Lightning. Okay? Lightning. So let me explain the phenomenon of lightning, because that is very much to do with my research work. Lightning, it has charge in the cloud. Yes? In the cloud. Charge can be generated in the cloud. Now you ask me, how does the charge get generated in the cloud? That's the Mother Nature, okay? And that's, it just gets generated, right? Because of the nature. So you have a lot of charge. So that means it has a higher potential, right? Here. And the Earth is a place, it does not have any charge, so it's a low potential, yeah? Okay. So somehow this charge will tend to go from here to here, correct? But as I mentioned, in order for the charge to flow, you must have a conductor between the two. Is the air a conductor or insulator? Huh? It's an insulator. Why? Because if the air is a conductor, all of you will be dead. With so many high voltages around us, right? So the air is an insulator. But how do we see the lightning? The reason it's the lightning is because of the flow of the charge from the cloud to the earth. Okay? The flash, you see, that is the current. But if the air is an insulator, how can the charge flow? It violated my principle of current. Anybody can answer that question?
It's arcing. It's arcing.
I know it's arcing. But why? Why does it happen? So I guess a more relevant question is, how can the air go from the insulator to a conductor, right?
It's very hot.
How? It's very
It's very hot.
hot. It's nothing to do with temperature. We do see some lightning in the wintertime. Right? Okay, now here's a very important concept, and I thought you had learned that from your physics, but apparently you did not. And this is a life and death concept you have to know. Okay? Any incident can become a conductor when the voltage becomes sufficiently high. And that phenomenon is called the breakdown. Okay? That's why people got killed when the person is touching a high voltage wire with a wood stick. A wood stick. How can the wood stick conduct the current? Because the wood stick breaks down. The same concept for the lightning. When you have more and more cloud, you have more and more electric field, right? When the electric field becomes very, very high, the air breaks down. And at that moment, it becomes a conductor, and then you start to see the lightning, so that's when the charge flows. Right? So this is a very important concept. So you don't never touch a high voltage wire with something you think is safe. It's not safe. Right? Okay. Okay, now, in terms of the voltage and current, there are two types of voltage and current. Okay. The first type is called the alternating V and I. Okay, so voltage we normally call V, okay? Capital V, and current we normally call capital I. So for this type of voltage and current, if you look at the waveform, the waveforms of the voltage and the current versus time, then they are changing. Okay, they are changing with respect to time. So this is called alternating V and A, and we have a name for it. It's called AC. Okay, or the reason called AC is called the alternating current. That's called capital A, capital C. It's not air conditioning. Okay. But the second type of the signal is called the direct V and I. Okay, so if you plot the voltage or the current versus time, then the waveforms are constant versus t. So this is also sometimes called DC, right? Direct current. Okay, I'd like to next talk about the symbols we'll be using for the class and the unit. K to represent that unit. V is the voltage, and the unit is volt for capital V. W represent the energy, and the unit is normally in joule, capital J. And P represent the power, and the unit is in watt, capital W. So when we have a circuit, we are mostly concerned about the current, the voltage, the power in the circuit. Sometimes we talk about energy, but it's not a major Okay, we also have the circuit components. Symbols. Huh? This is the symbol for the resistor, R. This is the symbol for the capacitor, C. And this is the symbol for the inductor, L. And in addition to that, you also have the voltage source symbol. Okay, for example, it has 10 volts, right? So that's the voltage source. Okay. So now, what's the voltage source in the real life? The battery, right? We use a lot of voltage sources in our electronic system. For example, your cell phone, right? It has a voltage, it has a battery, and that battery is about 3 volts. Okay, so that is a voltage source that can be used to power all the circuits in the cell phone to make it work. We take out the battery, what happens? Does not work. We also, in the circuit, we have the current, for example, in amp. So this is called the current source.
Is that an arrow?
Yeah, that's an arrow, and that indicates the direction of the current.
Okay.
Yeah. And you can see on the voltage source, I have the plus and minus. That indicates the polarity of the voltage source. Right? When you have a battery, you know there are 2 polarities, right? The plus and minus. That's it. There is no first polarity. So always plus or minus. That's it. All right. And sometimes we can also have what we call the dependent voltage source. And the symbol is this, plus or minus, for example. And for example, it's 10x, and the unit again is volts. Now, Now this X is a parameter from the circuit somewhere else. So therefore, it's called a dependent voltage source because the total value of that voltage depends on what? Depends on the value of X. So it's called a dependent. We also have the dependent current source. So for example, that's a dependent current source, 5Y in. So 5Y is the value of the current, but Y is a parameter in the circuit somewhere else. Okay. Won't get into the circuit that will become clear to you. Okay, I think that's all the basic background I'd like to give you. Now we can get into a little more details. Any questions so far? Okay, the first and probably the most important law for the linear circuit is called the Ohm's law. Okay, so let's say you have a resistor and it has a voltage, say V. Again, this voltage can be coming from the battery, right? Okay, let's say you put a battery and then you connect the battery with a resistor. Then you would have a current flow from the higher potential, right? Positive means it's a higher potential, negative means lower potential, right? Okay, so you would have a current flowing from the higher potential to the lower potential. Correct? And that is called I. And according to the Ohm's law, I is equal to V over R. This is very simple and obvious, huh? Somehow he was the first one that thought about it. So that's why the law was named after him. All right, so let's say I just give you a very simple example. Huh? Ohm. Oh, by the way, did I tell you what's the unit we use for resistor? Yeah, that's the unit for the resistance. Ohm, right? Okay. And let's say this is a 10-volt voltage source. Then we want to find the current, right? I. Well, so you can see that the voltage across the resistor is 10 volt, yes? So the current is going to go from here to here, go this direction. So therefore, I is equal to 10 volt divided by 10 ohm. That gives you 1 amp. Huh? Very simple, huh? I wish all examples would be so simple. Life is tougher than we think. Yeah. Not so simple. All right. Now, in the beginning, we're going to talk about the resistive circuit. Huh? So that means there are only resistors in the circuit. There's no capacitor, and there's no inductor. Okay. So that's the beginning of the chapters. Yeah. Basically, we're talking about chapter 1 to chapter 4. All these chapters cover resistive circuits. Okay. Now, of course, in the circuit, we cannot possibly just have one resistor. Huh? You can have multiple resistors. Huh? So what happens if you have multiple resistors? So there are two types of connections. First one is called the series connection. The second one is called the parallel connection. So I guess today we're going to focus on these two connections. Actually, our time is running out. All right. So what is a series connection? Well, just by the name you know what. Right? This is a series connection, R1, R2, and R3. Yes? So therefore, the total resistance R equivalent is equal to what? It's just equal to R1 plus R2 plus R3. Yeah? Okay, the number of the components in series can be unlimited. Yeah? You can have 10, you can have 20 in series, and this formula applies. Yeah.
What does that say after the R?
Oh, equivalent.
Oh,
So this is the equivalent of that. Okay. And again, the number of the resistors in series can be infinite. It could be any number. If you have 4, then this will be 1 plus 2 plus 3 plus 4. Huh? But you have to know that when you use this formula, each one of these has to be a single branch. What I mean single branch, maybe I should give you an example. Okay? If you look at this example, you have this is a single branch, right? But this becomes a double branch. And you cannot say, I don't know how you're going to say this. You cannot say this is R1 plus R2 plus R3. Okay, this is wrong. Okay, so the equivalent resistance cannot be calculated from this formula. Got it? It has to be a single branch, like what I have on the right. Okay, then when we come to this actually is called the parallel, the second type. Okay, so this is the second type, the parallel connection. So now you can see the difference between the serial connection and the parallel connection, right? The series connection is what? Is there's a common node, one common node between the two components. That is a series connection. For the parallel connection, what? You have two, right? You have two common nodes in a parallel connection. So what do you do when you have a parallel connection? So what is the equivalence of that? So now let me see just these two, huh? So this is a parallel connection, huh? So this is called R1, this is called R2. Okay, so the R equivalent is equal to, so that's the formula, huh, for the parallel connections. It's equal to 1 over R1 plus 1 over R2. Okay, so that's the formula. And again, the formula applies to any number of the components in parallel. Huh? For example, if I have 4, right? Then it can become a single resistor, and that R is equal to what? It's equal to 1 over, let's say this is R1, R2, R3, R4, right? Then it's equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Yeah? Simple enough? Yeah. But sometimes it's not so clear between the serial and the parallel. So let me give you one more example and we can start. Okay. So now we can see we have the combination of the series and the parallel connections in the circuit, right? Okay, and I want to find out what is the equivalent resistance in that box, right? So if you call this A and B, so basically we are looking for R, A, B, right? The resistance between the terminal A and the terminal B. Well, if you look at it, you can say, well, I have this one, and this one in series. Huh? Are they in series?
No, they're not.
Or let's forget about that. You can say R1 and R2 are in series. Yeah? So R1, R2 in series. Unfortunately, it's not, because we have something that is sticking between R and R2. And that does not allow you to use the series, the concept of the series connection. When you say series, that means I have this in connection, but I have nothing else in the middle. But I do have something in the middle. Can you see this is the same, the way it's connected, right? Okay, but you have R3, actually it's R3, right? R3 and the R4. Okay, so every time when you try to find the equivalent resistance from the terminal like this, you always try to go from the opposite direction and to simplify the circuit. So if you go from this direction, first you see these two are in series. Agree? Because there's nothing connected to the middle, right? Okay, so therefore, we can simplify the circuit, become like this. R1, R2, and this is what? R3 plus R4, right? Then these two are in parallel. So therefore you have R1, R3 plus R4 in parallel. Okay, that's the symbol of parallel. In parallel is R2. So therefore, the final solution, answer for the equivalent resistance is what? So RAB, which is the equivalent resistance, is equal to R1 plus this in parallel, so it's what? It's 1 over R2 plus 1 over R3 plus R4. Got it? Because that's the formula for these two in parallel. Huh? Okay, that's all we have today.
This was R1, right? R3 plus R1 divided by R1.
R3 plus, no, it was R3 plus R4.
R4.
Parallel to R2.